now I'm going to look at the control map, and I've looked at it already in the discrete time, but now I want to focus on continuous time. Because remember, the control map for the continuous time was a different beast altogether. And so we're going to look in depth at the control map and its brothers. Okay, so here's our control system. X dot is equal to AX plus BU. It's initial condition time at time t naught. The solution to our differential equation is given by this, where, again, we've used the state transition matrix and the control map to do this. And so, again, if we looked at the transfer problem would be, again, finding a control U from t naught to t such that this quantity is equal to this, where xf is some desired final initial condition. Right? Last time I had xd, so whether you call it xd or xf, it's basically that's the final desired state. And so the question is, when can I find the control signal to make this happen? Now, in the discrete time problem, it was fairly simple because this was just a matrix. Okay, this was just a matrix. In the continuous time problem, now, this is a convolution operator. And so we saw this before. We had this convolution integral that the control map satisfied. Takes something in our space U and gives us something in Rn. Okay, so we don't just have a matrix now. We have this integral operator, this convolution operator. So the space U is the space of functions from time t naught to t. So a particular U in this set, I can operate it on by B, the control map, and I get in a vector in this space x at time t. Okay, x at time t. I get an element, but it's just a vector in Rn. X at time t lives in the space of Rn. So if you recall, whenever we define an operator from one space to another, we can also define its adjoint. The adjoint that takes something from this space and gives us something in space. It's not necessarily an inverse. It's an adjoint. Okay, so in other words, the two spaces may be very different, and so you may not get the inverse back. So if you recall the adjoint, the definition for the adjoint of an operator, in this case, it's going to take something from Rn and give us something in the space of functions from t naught to t. Recall that the definition of the adjoint was that these inner products were equal to each other. So B operating on U is something in the space of Rn. So this inner product is an inner product in the space Rn. U is in the space of input signals, and so the adjoint on some vector in Rn operated on by B, this is also a function in this same space. Okay, and these inner products must be equal to each other. Okay, so we have gone through and shown, we've proved earlier that the adjoint of the matrix B, of the operator B, is given by this expression. The state transition matrix times B adjoint times the vector V. So notice we actually are operating on V, which is the input space to the adjoint. Okay, it's some vector in Rn. And so here it just appears here. And this is defined to be this function. So notice this is a function of tau and actually t, because t appears explicitly in here. And so, but for values of tau between t naught and t, this is the function. When t naught is outside that range, we get 0. So this is how we can define the adjoint of the operator. We've seen this before, and we actually went through and proved that this, in fact, is the adjoint. So now, and so the reason we're doing this is because we want to be able to solve that transfer problem. And so, just like with the discrete time problem, we required the adjoint. In the case of the discrete time problem, remember the control map was just a matrix, and so its adjoint was just a matrix. In this case, no such luck. We can define the controllability Gramian that takes something in Rn and gives us something Rn. So whenever you'd have something that goes from Rn to Rn, basically that's a matrix. Now, in this case, the matrix is a little more complicatedly defined. So it's basically this operator. it's B operating on the output of B adjoint. So remember, B adjoint is an operator. It's going to operate on something. And B is an operator. It's going to operate on something. So we can actually think of it this way. This matrix times V is B adjoint operating on V. That's going to give us a function in this U space. Okay. And that function in U space, we operated on B, and that gives us a vector in Rn. So V is a vector in Rn. We end up with something as a vector in Rn. So altogether, however, it is just a matrix. We can also show that the energy associated with V is given by this expression. We can go through and show that. And K, the Gramian, instead of being formed this way, as if we had to operate on something. So the way it's defined here, it's actually a conjunction of operators. That is, B adjoint is actually going to be operating on something, but B then operates on whatever comes out of that. So it's defined in terms of an operator. Turns out we can actually define it without an operator this way. Okay, so it involves the state transition matrix and B. Okay, so, and it's the integral from T naught to T. So this is the controllability Gramian. So it is more complicated than what we had in discrete time, but actually it's not that much more complicated. Here I just have this integral, and the state transition matrix for a linear time invariant system is just e to the at, and so it's actually not that bad. It's not actually that horrible, let me just say. It's not that great, but it's not that horrible. Okay, Gramian has some properties. Okay, so for t less than T naught, the Gramian is 0. If I take the partial derivative of the Gramian with respect to time, I get this expression. Okay, and if I look at what this expression is, notice it involves the Gramian, but this is like a Lyapunov equation, a continuous time Lyapunov equation. So we have this relationship. We also have the fact this property that the Gramian from T naught to T can be broken up from T naught to T1, from T1 to T. We can break it up this way. So it's kind of like a transition property. So this is the case for continuous time systems, and so we have this result for continuous time systems. The system AB, system with matrices AB, is controllable on the interval from T naught to T if and only if the control map is onto. Okay. Now, in this case, the control map is a convolution operator. Yuck. How do we check the onto-ness? Well, we also have this fact. So basically, onto means that the range of this matrix is all of Rn. That's what it means. So again, how do we check that? Not so easy. Here we can check it this way. The range of the control map is equal to the range of the Gramian. So this is the way we would actually check it, because the Gramian is something we can actually get our hands on. And so we have this. AB is controllable if and only if the Gramian is positive definite. Okay, so having defined the Gramian in discrete time kind of gave us a clue of what we can do in continuous time, but clearly in continuous time things are more complicated. We can also define the pseudo-inverse. So we've defined the adjoint, okay, but the pseudo-inverse also takes something from the same space and gives us something in the U space. Okay, so it also defines that way. And we can define the adjoint this way. It's the control map adjoint operating on the inverse of the controllability Gramian as an operator. Okay, and you can go through and show that this, in fact, is the pseudo-inverse of B. But it requires, notice, that K be invertible. So it requires that the system be controllable. So having defined it this way, we can go through and show that the control map operating on the pseudo-inverse is in fact an identity matrix. As long as K is positive definite, then this is defined, and so we actually get this. That is, the control map pseudo-inverse is a right inverse operator for the control map itself. So there's a lot of complicated stuff going on here, because remember, B itself is a convolution, so it's actually convolved with whatever the output of this is. This is a function defined from T0 to T. So it's fairly complicated, but when you see it in this form, it's like, yeah, that's simple. And actually, we had the same kind of thing in the discrete time. So there's a lot of parallels. So having looked at the discrete time first greatly simplifies working with this thing. Finally, we can look at what's called the infinite horizon linear time invariant Gramian. And so if A is Hurwitz, then this integral converges, and we have the Gramian given this way. So we similar to discrete time. In discrete time, we had to have the system stable, which is the spectral radius less than 1. In this case, A has to be Hurwitz for this integral. So spectral radius less than 1 was required for that infinite summation to converge. Here, the A being Hurwitz is required for this integral to converge. This integral then, K, that satisfies this integral, satisfies this Gramian, this continuous time Lyapunov equation. Okay, so this continuous. So we see again parallels between what we saw with stability, what we saw with controllability. We see a lot of those parallels in discrete time as well as continuous time. So in summary, controllability is the ability to apply a control that will take us from any initial state to any final state in finite time. In general, this requires that the control map have a full range, that is, all of Rn. The range of the control map can be examined using the left eigenvectors of A. The controllability Gramian can also be used to assess controllability. And the Gramian, at least for a stable system, can be given as the solution of a Lyapunov equation. So we have some of these nice properties. So this is our introduction to controllability. Stay tuned now for some practice problems.